Salutations. We continue with our applications of first order differential equations. And this section is called elementary mechanics, but it's actually really about gravitational forces and Newton's second law of motion. So you see, Newton was very active, right? Newton's second law of motion. So it is, of course, again, a rather ideal model where things could be much more complicated, but let's take a simple case here. We have an object that is moving on a line. And since we're dealing with gravity, although there will be a homework problem where it's something else, but about a boat that is traveling on sea, that would be horizontal. But for most of in our situation, our movement is vertical, either going upwards, a rocket, or falling down. And so we will mark the position by y where we choose, depending on the problem, our starting point, the origin. Okay, so y indicates the position on the line here, and then so that means what is the velocity? This point when this object is moving. We know that under gravity, as I said, most of it will be about gravity, so I'm going to just keep talking about that. That an object starts falling, but the more it falls, the faster it falls. So, in other words, the velocity is playing a role here. So, y prime, that of course the variable here, so the variable, of course, is always going to be t, time. Measured in minutes, seconds, depends a bit on the problem again. And units, I'm going to be a little bit vague on units very often, although one should be careful. But y prime is just the velocity. So that's the velocity, right? That by definition, velocity is just the derivative. But Newton's second law of motion actually doesn't talk about, it's not about velocity, but even more so, it is about the acceleration. So a acceleration. What is that? Well, that's the derivative of v, which is the double derivative of y. Okay? So these are our object, the quantities that we talk about. Now, this object here, so this is an object, this will have a certain mass, because also that matters. You know that if you, well, an object will, depending a little bit on, when we talk about gravity and the motion under gravitational forces, we really have to make a distinction between two cases. The case that one often thinks about is gravity as we are here on the surface of Earth, when you fall out of a tree or something falls off a roof, or you shoot up a little rocket, toy rocket up or something like that. There the gravitational field is kind of constant, and therefore, as we will see, it's kind of, your mass doesn't really matter. However, when you are talking about gravitational forces in a more cosmological point of view, so from rockets not just going up and down here in near the surface of the Earth, but going to the moon, say, then the gravitational forces work a little bit differently, and mass is part of it. Now, what is Newton's second law of motion? So let me write down the law here. I'm gonna box it here. It's a very simple law. It says F equals ma. Now, a, we already said, that's the acceleration. M is the mass of the object. What is F? So F is the force. So what Newton says, you should think about it this way. It says that if you have an object with a certain mass, and it's sitting there, just nothing has happened to it, but all of a sudden a force is applied to it, what the force will do is it will not make it, it will not, it's not, it will change its velocity, but even more so, it is related to its acceleration. It makes the object accelerate. Okay, so think of it, if you're standing and somebody is pushing you, your velocity changes, of course you're going to start start moving forwards, right? So say you're sitting in a little toy car and somebody is pushing you, and so the car starts moving, but you start from zero velocity to a certain velocity. So that means a change of velocity means that there is an acceleration that is taking place. Sorry, and that is what Newton's very simple observation is, and he basically says that the force that applies to an object is proportional to its acceleration, and the proportional constant is that what we call mass. Now, because I mean, you might say, oh, mass is that's how much you weigh, right? Yes and no. Mass is an intrinsic thing, is an intrinsic property of an object. Weight is how much we weigh here down on Earth. Okay, but you know that if you're, well, you don't know, but you probably have heard that if you're on the moon, you kind of weigh less. So, in other words, but you haven't changed. So weight is not intrinsic property of you, it is mass. Okay? So let's start with unraveling that part, because I must admit that was something that puzzled me for a long time too. But let's say the ideal gravitational force, that means ideal means that we are in a vacuum and nothing else is happening. That is simply given by, then if we are near surface of an object, near surface of a stellar, like a planet or a moon or something like that, that is constant. The acceleration is constant. So g is the constant, and I'll emphasize that. Acceleration due to gravity on ... Of course, we're thinking on Earth, but you can do this on the moon, you can do this elsewhere, okay? And so, sorry, yeah, so that's so in other words, if we are, as I said, there's a difference between near an object and on the surface of the moon or the Earth, or somewhere down in space. Why? Well, it's not entirely correct, because if we would to bring the moon very close to the surface of Earth, bad things are going to happen. But we are talking often with small objects, us, or a rocket, which is extremely small in comparison to the Earth, so that for all intents and purposes, it is only the Earth that exerts a gravitational force. But in principle, every object has a gravitational force. So us, we are also, when we standing here, we are actually attracting the Earth. We're putting a gravitational force on Earth, pushing it upwards a little bit. Okay? But don't worry, you say, oh, I should not move too much because then the Earth is going to shake. No, you're way too small to do anything with the Earth. But in theory, it is there. And therefore, but since the differences are so big, we just say, well, the acceleration due to gravity on the surface is constant. Okay, so what is then, if we do this in the second law of motion, so we see the force is a constant force, that is m times g, and so now we have to equate these things, so we have mg, this is the, remember, let me box this one here, this is the law of motion, okay, this is the, if you want, the gravitational force on the surface. Okay, so mg is equal to ma, and we see therefore that g is a. The acceleration is a constant. And for instance, g of Earth, depending on which measurements you use, let's use a simple one where it's a nice number, 32 feet per second square. You can think about why is it the second square here, but we'll not go on to that. Or if you want in so meter per second is 9.8 meter per second square. And so this means that y double prime is, well, okay, we have to, one thing of course is, we're choosing y to be representing the position, but we can make the direction of our y-axis either go up or down. I kind of hid it a little bit by putting my arrows in both sides, so let's we really should choose one direction only. And it's very common just to take the upwards direction. That is how we're standing upwards. We are people that standing upwards. We stand on our head is above everything. So that's why we always think upwards rather than downwards. So of course, we have to take that into account, and therefore we get a negative sign here, because gravitation will go against the direction that we have chosen, the upwards direction. It goes downwards. Okay, that's why it's this. Now, and this is a differential equation, if you want, that governs the free falling motion. Ideal gravity force, free falling, they call this also. And this is something you solved in Calc 2, in Calc 1. It's just an antiderivative problem. Of course, it's a double antiderivative problem, because you have to first do it once and then twice. Okay? Now, what is it in general? So in general, we will have here, so let's now look what this means in general. F is ma, and a is the double derivative, so this is my double prime. And so this f here, this will normally be a function of the force that acts on a particular object. That can depend on many things. It could depend on time. Like, for instance, there is an engine in there, or there is a force, an external force pushing it up or pulling it down. That depends on time. That is like, let's say, I don't know how to imagine that too much, but it also could depend on the position. Perhaps if you're higher up, the force is less. Let's say, I don't know. Let me not give too many things, and I will do examples later. And it could also depend on your velocity. And in fact, that's what it often does. So if you look at this, if I write it this way, so let me write it here, my double prime, and then we divide by m if you want, you see that you get a second order. This is a second order differential equation. So Newton's law of motion, if you want to solve in very general situations, you need to solve second order differential equations. So this is a segue into what we're going to do. Our next session is actually about that. So why are we talking about it now? Well, very often the position and even time do not matter that much. So often the force only depends on the derivative of y under the velocity. So the force is depending on velocity only. We'll see many examples of that. Okay? Of course, the special case of what we free falling motion, where it depends on? Well, it depends on this f here. So this is the f that we're talking about. In general, looks like it could be a very complicated expression, but here it's a very simple expression. M is a constant, g is a constant. It's a constant. Okay, so here it doesn't even depend on velocity, but we'll immediately see an example where it does depend on velocity as well. And then, of course, if that's the case, then, okay, we have to think, therefore, so we have to think of y double prime. Remember that y double prime is actually the single prime of v. And so this becomes then a linear differential order, not linear, a first order differential equation in v, in velocity. And that's why I'm gonna use it here. Okay, so let's go immediately to an example here that hopefully makes it much clearer what is going on. So, so what was it that I was going to say? Okay, yeah, let's go over this here. Yeah. Suppose we have an object and it has a certain mass. I'm going to keep the object as a. I'm not going to give a value to it, just a mass. And it is in a gravitational field, let's say of Earth. Let's say G is the gravitational constant. So we are somewhere in the universe on the surface, let's say, of a particular star, moon or planet. And we have this gravitational constant, G. If it would be Earth, it would be the number that I just showed you here, right? It would be, there's a table here, perhaps let's box it a little bit because I'm going to come back to it. So, and moreover, it's that object is in the free falling motion. We were going through a vacuum. So why? Because vacuums don't do anything. They don't change. They don't affect the gravitational force. But normally you go through air or an atmosphere, or perhaps it could also be that you're falling in water and you're sinking down, right? That's the same thing. So you have a certain resistance. And so here we have, suppose that the resistance is the resisting force, resistance, you understand what resistance is, right? So this what that a force that kind of slows down the motion. And we will think about it when we get to the sign of it. And so what resistance is proportional to the speed of the object. And that is not so surprising. Think about it. Let's think about just us running in windy conditions, headwind. If you're running at 10 kilometers per hour, if you're putting out a force of 10 kilometers per hour, but the wind is so strong that you actually only go 9 kilometers per hour, right? Let's think now what happens if you increase your speed to 20 kilometers per hour. What do you think? You're going to be 1 kilometer per hour less, because that's what's happened. When you were running 10 kilometers per hour, you only move forwards at 9 kilometers per hour, so a difference of 1 kilometer per hour. Do you think it's the same when you do 20 kilometers per hour? No, it's going to be the resistance is going to be doubly that much. It's going to be 2 kilometers per hour. So you're going to only run at the speed of 18 kilometers per hour. You're going to move forwards. Okay, so it is proportional to speed, not constant or anything, or it's not a constant difference. It's proportional to speed. So this is something that we often observe. Although this is it depends on the medium sometimes where we go. But let's assume we are now something where the resistance is proportional to speed. Okay, so let's write down the force. So what are the forces? Force or forces, perhaps, because there are several forces. The total force F. Well, so an object is constant on a relative force through a medium that exerts. Yes. Okay. Right. So what is the total force? There are two forces working on you. There is the gravitational pull, and since we said we're going to take our y-axis always upwards, this will here be minus mg. Remember, since we are dealing with a near surface, the gravitational constant, the gravitational force is considered to be a constant and is minus mg. And then there's the second one, so there's the resistance force here, Fr. Oh, let's just call it R here. Plus, no, not R, because that's going to be confusing. Because later we might do radius or something. So I'm going to just call F res. F res. Now, what does it tell us? They say it is proportional to speed. So this is mg plus proportional constant k. So k is this proportional constant times v. Now, is it plus or minus v? Well, it depends. It actually doesn't matter. Well, no, sorry, it doesn't matter. But again, yeah, the problem is that velocity is, when we say velocity, we actually mean the absolute value of the derivative. Okay, in daily parlance, in daily usage, you don't say you're moving with 50 kilometers per hour north, or you go 50 kilometers per hour south. But if you would work on an XY axis, a Y axis that goes from south to north, like we're pointing upwards here, then going down at 50 kilometers per hour would for us be minus 50. Okay, so we have to take into account here the direction of the velocity. Okay, and so the force So yeah, I won't want to go too much in the details of this. They explain it a bit more in the book if you look at both possibilities. So we like our constants to be positive constants, although in principle a constant can be negative, right? But one often prefers to write formulas that the constants are positive, and then we have to write a negative here because resistance is presumably slowing down the movement. Okay, so let's think about it just simply like that. It slows down the movement, so we get a negative here, right? When would we have a positive here? If we would have a little engine that pushes us, that it makes us go forward. But resistance is something that slows down. That's what the word resistance means. So that's why we have a negative sign here. Okay, so this is the force, the total force. So total force, let me write it that and then don't write the S here anymore. Oh. Okay, and so now we have the second, now we put down the law. What does the law say? I do it in green. F is equal to my double prime. I'm going to write, or y double prime, no, wait, sorry. Let me write it down originally. This is the original formula. This was Newton's law, right? No, why did I do that? That was make it very ugly. Let me do this way. Okay, so, but we know that A is actually the derivative of V, and I already mentioned here that very often, although in principle we will have a second order differential equation, if we think of it as a differential equation involving only velocity, if that's the case, and this is now the case, right? Because I just said the only thing, it depends on velocity, the resistance, and gravitation is just constant, doesn't depend on anything. So this is actually only depending on velocity. So if I look at it that way, I can think of it as the force is mv prime. Now, this is the law, and this is the actual force. You have to understand this a little bit, what's the difference here. This is the expression that gives me the force, in other words, what gives me the left-hand side. This is always the same. This is what the law says. The law of mechanics, this mechanical law of mechanics. So what we get is mv prime equals minus mg minus kv. And so what we see here is indeed a first order differential equation. It's actually linear. It's actually linear, so we know a bit how to solve this. Let's do this. I'm going to write down it in very general terms. Okay. First of all, we need to step one is the complementary homogeneous one. Then what does that mean? So you have to recognize here now, you have to think a little bit in your variables, right? So what is the variable here? T, of course, and then the function is y and y prime, and this is y. So so these two guys form the complementary homogeneous. This is the f that we have. In this case, it's a constant, but that is the non-homogeneous part. Okay, so the homogeneous or complementary homogeneous is mv prime equals minus kv. I deliberately didn't put in concrete numbers here because I want you to understand what each of these letters means. And not so much what they mean, but whether they are a function or a constant. And if they're a function, what they depend on. Okay, so that you recognize that we are dealing here, that this is the function and the derivative of the function. The variable is not present. So it's that's why it's a linear one, and all the other letters are constant. Okay, so going back here to solving this thing, so we know how to do this. We have to separate variables. Again, that's where it's important to know what is variable, what is not. So let's do this. So we have a dv over v, that would be putting all the variables on the side, and minus k over m dt, because t is our variable here, right? So, okay, if you want, let me do an intermediate step if you get a little bit confused. First, cross multiply, or whatever you call this. And then I prefer to write it this way, because then I know how to integrate. This is just ln v and this is minus k over mt plus a constant, let's call it d for the moment. Yeah, now a lot of letters are coming in, so make sure that you don't double up on the same usage of a letter. Okay, and we have to solve for v. So v is e to the minus k over mt plus d, and then the trick as always, ed e minus k over mt, and this we call a c. So our homogeneous solution, that we are not homogeneous here, is the general homogeneous solution is c e minus k over mt. Now, step 2 is a particular solution, but to the actual differential equation. This was to the complementary one, which is not the actual one. So remember, the formula v particular is UVH. Okay, so in this case, again, dropping the particular here, the p for particular, we're going to solve it. V is equal to u times this quantity here, because I can take c to be anything I want, and of course I'm going to take it equal to 1 in this case. Okay, we know now that we have to find u. We're going to get a separated simple separated variable. So we take the derivative. I'm going to plug this in. So this is u prime e minus k mt plus u times the derivative of the inside function. The derivative of the second part is of course e, plug in the inside function and take derivative of that, and that's what the result of this is. And now we plug this into our differential equation, which was here. Okay, so we have m u prime e to the minus k over mt plus m. Remember, I'm multiplying this whole thing with m, right? So we have mv prime equals minus mg minus kv. Okay, so I'll copy the equation. So I'm multiplying this quantity with m. That means that this in the second term, the m will disappear. So we have a minus ku e to the minus k over mt equals minus mg, that is just a constant, minus k times v, which is u e minus k over mt. This is where I get this from. And we know that some cancellation has to happen, which does happen. Here we see these two guys disappear, and so our equation is mu prime, and we're going to separate the variables again, right? So let's bring this to the other side, and that becomes a positive exponent, equals minus mg e to the k divided by mt. Notice that the m's cancel here, so we get actually du equals minus g e k over mt dt. That's our differential equation. That's after separating variables. So we integrate. We get u equals minus g, and now, as always, right? And the derivative of e5t is you take the same thing, but then divide by that constant in front of t, because you have to compensate for the chain rule when you take derivatives. So this is what I do here. So e k over mt divided by this k over m. That's the compensation rule. It's not a power rule, it's a compensation rule. Plus a constant, but we only need one particular one, so we don't bother about that. So we see that u is equal to minus g m over k. I flip this over to bring it up here. E to the k divided by mt. Now if I plug this in my u, v, so remember v is u e minus k divided by mt, right? That's this guy here. And so this now becomes minus gm divided by k, and all the e's cancel each other out. So I see actually we get a constant velocity here. Okay, but that is the particular solution. That's the particular solution. So the general solution, again, what is the formula? I do it in green, the formulas. Yeah, I should have done this formula in green too here. This was a formula, right? The formula is that the general solution is the general homogeneous solution plus the particular solution. So let's write down what all this is. So V is equal to, the particular solution is minus gm over k. I'm writing this first because I have it right here. And the general solution was this guy, c plus c e to the minus k over mt. There we are. This is, at any time t, we have our velocity here, given by this equation. Okay? Oh, sorry, I made a mistake, right? Did I plug in? No, no. No, it's correct, it's correct. I'm sorry, yeah. No, I got everything correct. So, of course, now in concrete cases, we can try to plug in these things here, what is what, right? So let's look at an example here. So, example of this situation. A 960-pound object initial upward velocity of 60 feet per second. So it has an initial velocity that it moves upward. So we can imagine this somewhere. This is the object here. Let's think of it as a rocket a little bit, right? And it has an initial velocity, makes it go up, but there is an air resistance that will work on it. And so let's say that let's say that k here is 3 pound per feet per second. I'm not going to take the units. So the constant of resistance, so this is the resistance constant, is 3, right? And what else? That's it. So we have this object. This is 960 pounds. And we're going to have to move this. It has an initial velocity, what did I say, 60 feet? So the velocity here is 60 feet. 60 feet per second. I'm not going to write the units. I'm just going to trust that all the units are matching. Okay? And, right. So let's plug everything in. Okay. V is G. We know what G is, right? G is, in this case, 32. Okay, with the minus sign is already taken care of that. So the gravitation constant is G. K also we have been given is 3. What is M? Professor, 960. It's the mass, it's the weight. Did we say that's how weight is? Remember, weight and mass are not the same thing. We think they're the same because we only on Earth, but remember, if your mass doesn't change when you go to the moon, but your weight changes. Okay, so what is that then? What is your mass? Well, let's just write down what it is, right? We know that, so what is the gravitational force? Weight is what the gravitational of Earth pushes your mass down onto the scale, say. Okay, so F is mg. Okay, and the force, that's what we say. The weight is actually a force. 960 is m times g, which is 32. So your mass is actually 960 divided by 32, which is 30. So if you want to calculate your mass, you actually have to divide it by 32. If your mass is 960 pounds, you divide it by 32 to find your actual mass. Okay? So this is the mass. Why we need this? Well, you don't need it here because we just said, right, that mg is exactly your weight. The force that the Earth pushes on your mass, that is what you conceive as weight. It's the force on which you've been pushed down on the scale, and that's why the scale reads 960. Okay? What Gm is therefore just your weight here. So if you plug in the first thing here, V is now minus your weight, 960, divided by k, which is 3, plus c, which we don't know yet, minus, but here we see, we didn't need to really know our mass there, but here we needed the mass for this formula, minus 3 over 30. Okay, we need to plug in, I'm plugging this one here, I need to know my mass, not my weight. In this part, it's the mass, not the weight that matters, T. Okay, so that's the general formula. That's actually simplifies like it's minus 320 plus c e to the minus t over 10. There is still something missing, right? There's a c here. Where does the c come from? Well, we haven't used, what have we not used yet? We used this, we used that, we didn't use this one yet. So initial velocity, so that at t equals 0, v was, and it was pointing upwards, was 60. It was an upwards. If we would have been thrown down, it would be a negative, yeah? So be careful there. So we get 60 equals minus 320 plus c times e to the 0, which is just 1. So we see that c is equal to 380. Okay, and so in conclusion, at any time t, we can figure out our velocity is given by this formula here. Now, of course, if you're falling down, you're going to hit the surface of Earth. So terminal velocity is a little bit weird thing to mention here. Terminal velocity would mean when t goes to infinity. But you're not going to fall indefinitely. But you could ask, suppose that somehow, this is a theoretical experiment only, but we still can ask this, and that means we would have to take the limit for t going to infinity. Now remember always e to the negative minus infinity, this will be 0, and we see that our terminal velocity will be minus 320. So at some point, because of the resistance of Earth, it's not a free falling anymore, there is a resistance. If this keeps going, that our speed will be around minus 320. Now you say that is theoretical, Professor. Why is this useful? Well, let's see how much what happens after, let's say, this t. I don't know, remember anymore what our units were. I think t was measured in seconds. Okay, let's see what our velocity would be. Let's say after 1 minute, so 60 seconds. Sorry. If t is 60 seconds, what is our velocity then? Okay, we can write it down. V of 60 is minus 320 plus 380 times e to the minus 6. Now, e to the minus 6 is a small number, very small number. Okay, you want to know how small? Okay, I'll tell you. 6 with a negative sign, e, this is about 0.002. If I multiply that with 380, that is about, so this whole quantity is less than 1, is 0.9. In other words, after 1 minute, you haven't reached the terminal velocity, but you're very, very close. Your velocity is minus 319.1. Okay, you're almost at your terminal velocity. So it still makes sense to talk about it, although we never will reach it. Very soon we will be very close to it. So if you're high enough that you can fall a minute, which is quite long to fall. I mean, you have to jump out of a plane or something like that. But you see that you're reaching a certain velocity here. So somebody that jumps out of a plane, and supposing that this is the conditions, I don't know exactly whether this is the exact model that would model this, but if you jump out of a plane, skydive like that, without a parachute, of course, but the parachute, of course, will change. What will the parachute do? It will drastically change the resistance. The resistance will be much bigger than slowing you more down. Otherwise, you would splash on Earth, right? Because if you don't have a parachute and you do free fall, you're still going by quite a serious speed. Minus 320 feet per second. I don't want to tell you how fast that is, but it is awfully fast. Okay. Let's go to one other problem. There are two things two more problems that I want to go over with, but I have to go a little bit faster by this. So we can now do the same thing. I'm actually going to leave this for the homework problem. So very often what happens in atmosphere apparently is that it's not proportional to the velocity, but proportional to the square of the velocity. So how would that change our initial differential equation here? So the only change, so I'm going to do this here, is that this would be a v square. But of course that changes drastically the calculations here, and so I want to leave that for you to investigate a little bit what the effect of that would be. So this is an example that I will work out as a homework problem. Okay, but so to do this example with the square here, for instance, go look at example 4.3.3 on the book. Okay, I want to do one more problem where it is different, but it shows you something perhaps that interesting also. All right, so okay, this is what is called escape velocity, and let me explain what this is about. Escape velocity, it sounds like cool, right? It's something, how fast do I run to get away from the cops? Where are we getting away from? This of course applies to rockets trying to leave Earth, in other words, to go to the moon, for instance. So if your rocket is not going fast enough, it will not be able to counter the effect of gravitation. Now, there are two things at play here again. Here, imagine, I'm going to make a couple of sketches here, but it's okay. Here is the Earth, and here is your rocket. Of course, that's not in proportion anymore. And the rocket is going upwards. Now, around Earth, my Earth is almost flat. Okay, I'm very bad at drawing circles. But so around Earth we have an atmosphere, and the atmosphere, as we said, acts like a resistance, like proportional to v or proportional to v squared. There's a couple of models that we can look at, and that of course slows down the speed of this rocket. Okay. But at some point, we're going to be high enough. Suppose that our rocket is going fast enough to go past the resistance of this atmosphere, and we reach a point where the atmosphere doesn't bother us anymore. In other words, there's no resistance of the atmosphere. If you're high enough in the stratosphere, the air is so thin that it doesn't make any resistance. Or you could also think of this. The model, of course, this was important when escape velocity was how to escape from Earth with a rocket to go to the moon. Now, once you're on the moon, you're actually luckier in the sense there is no atmosphere. So there you could do this from the surface of the surface already. But what normally happens if you watch these movies of launching rockets, you see that there's this huge, enormous fireball that comes out of it and pushes this thing up. And then at some point they say separation and burnout, and the actual engine falls down and doesn't do anything anymore. There seems to be no engines anymore. What has happened? Well, this burnout, this at this height here, this is called the burnout. In other words, you have used all your fuel. Now you have a certain velocity at that time, and you're luckily at a point that air is not going to slow you down anymore. So the only thing that you still have to worry about is gravitational pull. And so this is now the question: what velocity? So what v should I have at this moment when I'm out of the atmosphere and I have no engine anymore? In other words, I cannot accelerate anymore. Remember what these engines do, what this rocket fuel does, is it accelerates you, right? You're standing on Earth in the launch pad, and all of a sudden the big fire comes out and it pushes. You start pushing up. And if you watch these recordings of launchings of rockets, the rocket in the beginning it seems like it's just shaking and it's going up a little bit, but the higher it goes, the faster it starts going, and all of a sudden it's a small little dot. It accelerates. The engine makes it accelerate. It has to accelerate because it has to fight the acceleration that comes from gravitational pull. Okay, but at some point, all the fuel is burned out. The burnout moment, they drop that huge tail. I mean, these rockets, they are 90% is just engine and fuel. It's just a little top, the what do you call that? Uh, I'm drawing blank on the name of the cockpit, but it's not the cockpit. It's something similar. That is the only thing that remains. But that doesn't have engine. Well, it has so-called thruster engines that can move a little bit and can slow down a little bit, but it doesn't have these huge forces anymore to accelerate at huge speeds. That time you have to have the right velocity. So let's try to calculate this, okay? So how are we going to do this? Well, okay. Now we have to deal with another force. Because once we are so high up away from Earth, the gravitational pull of Earth is no longer constant. Imagine this, we're going to the moon, right? And once we're on the moon, it's clear that the Earth is not really doing anything for us anymore. It's not pulling us up anymore. So the pull of Earth is diminishing as we move away from Earth. Okay? So it is no longer a constant. So the question is, what is it then? Okay? So the force that you have on an object. So I'm gonna now make remember this is my y-axis. I'm gonna put this y equals 0 is the surface of Earth, okay? So this will be the burnout point. So this is, burnout point, I'm not need to write it down. Okay, and then there's also the radius of Earth that is gonna matter here. Because the law of gravitation, the true law of gravitation, involves the square of the radius. So I'm just going to write down the formula. The formula, this if your little object is y here, which has a certain mass. So remember now the mass is going to be important. This is important too, right? That's why we have to balance these things. They're trying to make this as light material as possible to make this. Now, okay, you say, Professor, but you just told us weight is not mass. No, but it's related, right? It's given by this relationship here, right? This is the relationship between weight and mass. Sorry, and mass is given by the gravitational constant on Earth. So, making something lighter means also you're making it less mass. Okay, so what is the formula? I'm just going to write it down here. mg r squared divided by y plus r squared. So this is, and it is a negative force because of course it is still pulling us down. It is still, we're trying to get away from it. This is what it does. Okay. I'm not a physicist. This is not a physics class, so I'm not going to tell you where this exactly comes from. This is what I'm telling you. This is the force that acts upon this rocket here that is floating through space now. It has a certain velocity, and that velocity might slow it down and might pull it back to Earth. We need a velocity that doesn't do that. That's what we call the escape velocity. Any velocity, so the escape velocity is the least velocity you need to get away. If your velocity is below it, you fall back. If your velocity is highest, you are escaped. Okay. But of course, there are other considerations, right? You just don't want to escape. You're going to have enough speed to actually get somewhere. But that's a different issue. Okay, here. So let's write down now our differential equation. So this is the formula for the force. So what is now, again, that's Newton's law, but we have to write it now as a second order equation, second order derivative of y, of position, of height, if you want. So, okay, what is this? So, we're using this, in other words, we put this equal to this other expression. So, my double prime is equal to minus mg r squared y plus r squared. Okay. Now, you see that the m's actually don't matter here. I said this, but actually it seems to be not important here, right? Okay. It depends on the gravitational pull of Earth here. So, but you say it doesn't contradict what you say? No, it doesn't. But because remember, we're talking about weight, which is something that depends on mass. and g. Okay, let's not go to that issue. So y double prime is equal to minus r square y plus r square. Simple enough, but what's the problem? Oh, I forgot my g here. What's the problem here is that this equation involves y double prime. So this is a second order equation. I've pointed that out. So, but no worries, because in this most second order equations, this actually right. So here, let me go back to the original formula that I said where we might run into problems here, right? That was second, but it's that often the force only depends on the velocity, not on the position. But that's not the case here, right? Here it does depend on y. In fact, y prime doesn't even occur here. Now I'm going to do something that might be a little bit strange here, but let's think of this. So first of all, y double prime is the same as dv dt, right? The derivative of velocity. So let's do the following strange trick. Let's calculate, yes, dv dt. Now we know that there's a chain rule. One way of doing the chain rule is that, let me write it down and then we can discuss it. If you think of velocity as velocity depends on time, but we can think velocity depends on the position, which depends on time. Okay? If you think of this as a chain rule, where v depends on y, which depends on t, then the derivative of v with respect to t is the same as the derivative with respect to v of respect to y. So I'm thinking of v as a function of y, which is a function of t. Graphically, let me formulate the formula that I wrote down just indicates what depends on what, and that is the way that these things multiply. This is the chain rule. This is perhaps the primary chain rule, but we don't use it in that way. But I, for instance, when I teach Calc 1, I teach it this way first, and then I'll do the formula that we normally know with outside function, inside function. Another way of saying that is we can pretend that these guys here cancel out. Okay, so whatever it is. So again, this is something from calculus, so I'm not going to dwell too much on that. Why do I do this? Okay, dy dt is v. So v, this is dy dt is v, right? That's just v. So we get this formula. Okay. So what does this mean now? Let's write this. So in other words, I can replace y double prime by this quantity. So v dv dy equals minus gr squared y plus r squared. This is a first order equation in v. And this is a trick that we will later discuss more. This is reducing the order trick. And this is now something that we know how to solve. In fact, I think we can separate the variables here, right? This is v dv equals, and then everything else here, minus gr squared dy over y plus r squared. Okay, and let's enter derive. This is v squared over 2 equals, let's think, minus g and r squared are constants. And what is this then? This is, let me rewrite this. Okay, this thing is the same as y plus r to the power negative 2, right? So I'm going to write it that way. So I'm going to move my dy a little bit out of the way. Okay, I have to rewrite it. I don't want to do this. Okay, I know what's going on here. I put this too big. Okay, so what am I going to do? Yeah, I'm getting rid of this thing. Okay, now I'm good, right? dy. Okay, and now I can do the power rule on this, although it's not y, it's y plus r. We know that this little linear thing doesn't make a difference here. So this, by the power rule, this is add 1 to the exponent and divide by that exponent. Antiderivative power rule, okay? So where are we? So this means that v squared over 2 is equal to minus signs cancel, g r squared y plus r. And therefore, let's bring the 2 to this side, v squared is this, and therefore v, plus c, sorry, plus c here, let's plus d, let me call it d for the moment. So we get plus 2 times d, but let's write replace d by 2d, upload the 2 to the other side, and then get really technically a 2d. Okay, let me write 2d, otherwise you might. So what is v squared? So, oh, sorry, v is therefore the radical of this thing. 2gr squared over y plus r plus 2d, which I'm now going to call c. Let me see here. Is that how they treat the right? Sorry, no. Yes, okay. So what does this now mean here is, how do we make sure that we escape here? Oh yeah, so we have to calculate c, and c will depend on the initial velocity. So what is v0? So remember, what does initial velocity mean here? Our wait. Okay, I'm a little bit. What? Oh, okay. So yes, initial velocity, not at time 0. At time 0, we were on the surface of Earth, right? That part from the surface to Earth until the burnout was something that was governed by this extra engine that I have. So that was the force was there, not just given by this formula. By where was my formula? By this formula. This was the force that you have. But why was this? Okay, here, this force. So this force. This is the force that we have at the time of burnout. Before the burnout, what is happening? First of all, we would have a constant. We could take this. Let's not talk about this part. Here is the gravitational part, right? There would be a resistance part, but more importantly, there would be a positive contribution, a positive force pushing us up the rocket engine, right? So that force, this movement from here to there has a different differential equation, because there is a different force, is an extra force, but the force ends at this point. And so this is the point where we want to know what the velocity is, okay? So this escape velocity here is at the time of burnout. So the velocity, so v, let's call it v b, is the velocity at burnout. Okay? So at that time, we don't know exactly when that time is, but we know the position of that. So so we can calculate this. So let h be the height of burnout. So in other words, in my picture here, this distance here, this is what I call h. We are now h, whatever, kilometers above the surface of Earth, and that's the time that our engine stops burning. And that's at that position. So in other words, I have to put, so this is y, so this is height of burnout. So this means that Vb is the velocity, the burnout velocity is the velocity at that point. When I am at burnout, that's my velocity, right? So what is that? Well, we plug this in. The burnout velocity is, now plug this in, 2gr squared. Y is now h plus r plus a constant. Well, it is sometimes easier to find, so let's square both sides again. Vb squared is equal to 2gr squared over h plus r plus c. So we see that Vb squared, that c is the square root of burnout velocity minus this here. Okay, so yeah, the formula gets a little bit ugly that way. So let me not plug this into the formula. So this is our constant here that should be go in there. Now what I now claim to say is this. So claim, and again I'm not going to go to the details of it. If this is positive, if this is constant, if C is positive, then we will escape. In other words, if the burnout of the square of the burnout is bigger or equal to 2gr squared over h plus r, then we have, then VB is the escape, allows us to escape. That velocity, sorry, let me say it, I say it a bit wrong. I'll say it better. We need this to be positive, okay? And so the escape velocity is exactly when this would be equal. In other words, the escape velocity is equal to 2gr squared h plus r. Okay? So it depends. What this tells us? It tells us, okay, it depends on the radius of Earth. It depends on the gravity constant. And it depends on at what time we are stop pushing it. Okay. Now, if I said we might decide to do this at h equals 0 when we're dealing, for instance, with the moon, where the atmosphere doesn't really bother us, and then we see that the escape velocity, the square, this is a square, right? We see that the escape velocity would be 2gr. The square, sorry, v escape velocity is the square root of this thing. 2gr squared h plus r. Okay? That's the escape velocity. That follows from here our discussion, because when this is positive, why? Let me perhaps explain this. We have to take the limit for y going to infinity. Let's take the limit of this thing for y going to infinity. What happens if y goes to infinity? What happens to this term? It becomes 0, right? Because this is infinity plus something and there's nothing there. So 1 over infinity is 0 plus c. So we want a positive velocity here. So we see that c has to be positive here, right? Or rather v squared. We take plus or minus radical. So we should really reason here. Sorry, we should really reason at the square of the velocity, right? So if I take, let me write it up here. The formula with so v squared is equal to minus 2gr squared over y plus r plus c or dc. Let's call it c now again. So this was our equation, right? And if y goes to infinity, if we want to try to go away as far as we can, then this will become 0, and we see that this velocity will be given by this constant here. But that needs to be therefore positive here. Okay, so our constant has to be positive, which means that this quantity has to be positive, which means that the square of this velocity of the burn at the time of burnout must be bigger than this number. So this is the number. This quantity governs when is the cutoff between the square of a losing velocity and the square of a winning velocity. Let me put it that. So it's what we call the escape velocity. Okay. But it depends also on the position at which time you decide to let go of your engine and just let it flow through inertia, right? So remember this, why does it still move? Well, there is a force pulling on it, and the force, of course, is going to make this slow down. You see that this formula, as y gets bigger, is gonna make the number smaller, right? Because in the limit this becomes 0. So as y increases, this is going to be smaller and smaller. So our velocity is decreasing. We still are being pulled by Earth downwards, but not enough, right? In the end, since this is positive, we will keep going. Remember, inertia. What is inertia? That's perhaps the simplest law of motion, is where the force is 0, right? If the force is 0, then what happens then? Well, then the double prime is 0, y double prime. So v prime is 0, it means v is constant. And this is what inertia is. Inertia is when an object is moving at a certain velocity and not force is acting on it, then it keeps moving with that same velocity. Okay? And so, now of course, when you do this with an actual rocket, you're going to have to, you probably want to still increase the speed here, that you have enough speed to get somewhere, right? Because the farther you, if you want to fly to the moon, okay, you have to have a certain velocity. If you want to fly to Jupiter or even try to escape the solar system, that would be a new calculation, right? You would have to calculate the velocity that you need to have at the edge of solar system to be even get away from the solar system. If you think of the solar system now as one huge gravitational object, with the center centered, of course, at the sun and the mass given by the sum of the masses of all the objects in the solar system. But the same model applies. Okay, I'm going to stop here. I'm going to do some homework problems for you that you can test this out, and we do probably also a quiz on this.